Hi, everyone. Yeah, I'm Alex, third-year grad student working with Maria and Josh. So today I'll be talking about a radial velocity survey of strip stars in the Magellanic Clouds, which are in the background here. This work is part of a larger collaboration in between U of T with Maria's group and Ilva Goldberg at ISTA in Austria. And you hear all the people who are currently working on the strip stars along with me. So is the mic on? I'm hearing some echo. Okay, we're good. If you don't care about massive binaries, you probably should. And that's because 75% of massive stars are going to interact at some point in their lives. And a third of all massive stars are going to be binary stripped, where their envelope is removed through binary mass transfer. And this has a huge range of implications from stellar evolution to gravitational wave mergers, cosmic ionization, et cetera, et cetera, et cetera. So binaries are very important. Talking about strip stars specifically, up until a few years ago, this is what the number line of strip star mass looked like. So on the low mass end, we had subdwarfs, and then on the high mass end, we had Wolf-Rayet stars, and nothing much in between. And so the main question, which people were wondering, is where are the intermediate mass strip stars? Technically, one exists. It's very strange. It's magnetic. It might be a merger product, HD 45166. But beyond this one system, no population existed. These are objects which initially had main sequence masses of 8 to 25 solar masses, which have then become 2 to 8 solar mass strip stars after mass transfer. So how do you make a strip star? Initially, you have two main sequence stars, and the primary is just inside its Roche lobe doing its thing on the main sequence. And then it'll leave the main sequence, expand, and then potentially overflow its Roche lobe, at which point the secondary star starts pulling material off of it, stripping it. And then eventually, after this mass transfer process is done, you have a strip star and an accretor. You might notice that the accretor here has been spun up and also got bigger. That may or may not happen, depending on the configuration of the binary you have. So in theory, what should these strip stars look like, these intermediate mass strip stars, which I'm just going to shorthand as strip stars from now on. They should be very hot with temperatures of 30,000 to 100,000 kilokelvin. Sorry, 30,000 to 100,000 Kelvin. Compact with roughly solar radii. Very hydrogen poor because they've just had their entire hydrogen envelope removed almost. And of intermediate luminosity in between the subdwarfs and the Wolf-Rayets. So that luminosity here, where the strip star spends most of its lifetime, is in this intermediate regime. They have a variety of implications. So to start off, the subdwarfs can't explode as core collapse supernovae, and the Wolf-Rayets are not numerous enough to reproduce the rates of hydrogen poor supernovae we observe. So if you want to account for this, you have to invoke a strip star population. On top of this, depending on the UV output you assume for strip stars in the early universe, they can contribute 10 to 30% of the epoch of reionization energy budget. And finally, strip stars are gravitational wave merger progenitors. So here I'm showing an evolutionary pathway taking two main sequence stars to a double neutron star merger. And you can see that there are two phases of envelope stripping required here to make this scenario work. So Maria Ilva and Bethany Ludwig started a search for strip stars in the Magellanic Clouds. To do this, they used UV optical photometry. These are CMDs in both clouds. The reason why you want to use UV photometry is that the SEDs of strip stars peak further into the UV than main sequence stars. And so if you see something which is bluewards of the main sequence, this is potentially a strip star. And they followed up some of these promising systems, bluewards of the main sequence, and they found strip stars, 25 of them, which they published 2 years ago at this point. So this is all of the numbered ones, 1 through 25. A few things to note here. First, they're less luminous than the Wolf-Rayet stars in both clouds. They're all bluewards of the main sequence if you assume an average extinction across both clouds respectively. And finally, they seem to roughly align with the expectations for the core helium burning phase of strip stars, which is this line on either side here. So to summarize this discovery, 25 strip stars were identified with UV excess. They're all bluewards of the main sequence. When two spectra were obtained at different times, they all showed radial velocity variations, and they exhibited a range of relative flux ratios. Here, relative flux ratio means how much light the strip star is contributing relative to its companion. In some cases, the strip star completely dominates the optical flux, and in other cases, the companion is dominating the flux. In a sibling paper, they published the stellar properties for a subset of these strip stars. So these are the observations here, the observed spectra. And in comparison to the theoretical expectations, it all seems to jive. So these are Hertzsprung-Russell diagrams in both clouds, and you can see the evolutionary tracks here. They're all roughly landing where we expect core helium burning to occur. Their temperatures are in between 30 and 100 kilokelvin. Their luminosities fit, and they're in between the subdwarfs and the Wolf-Rayets. So this is very much in line with theoretical expectations. At the same time that they were doing this work, they were continuously monitoring these stars and measuring radial velocities with epoch spectra. This is an RV monitoring campaign which started in 2018 and has continued to this day. I came in halfway through this. So to do this, we've been using one of the 6.5 meter telescopes, one of the Magellan telescopes, and specifically we use MAGE, which is a single object optical Echelette spectrograph with a medium resolution. And in total, we've gotten hundreds of epoch spectra. And just to give you a sense of how much work is involved, it's approximately 1 hour of exposure time per strip star. So this means hundreds of observing hours over the past 6+ years. Many remote nights, which I've partaken in, and a few in person. So this is myself, Steph, Grondin, and Yu Yang. This past summer when Maria took us to LSU and we're posing in front of the mirror, which is like so humongous in person. It's crazy. So now I'll get to the work that I've been doing, which is trying to measure the RVs across time and eventually convert these into orbits. So specifically, I'm going to be talking about strip stars with dark companions. Here, dark does not necessarily mean a compact object. It simply means that they're dark in optical light relative to the strip star. And in the discovery paper, it was mentioned that we detect RV variations indicative of binary motion, but now we want to follow this up and quantitatively assess whether or not we're actually seeing binary movement and convert this into periods, eccentricities, and minimum companion masses for these systems. Okay, I would love to talk about the methodology of how you measure RVs, but instead I'm going to give you this poem, which reads, "Measuring RVs is easy, but measuring RVs well is hard. With limited time during tasty, methodology I must discard." And now we can go on to the results. So feel free to ask me about the method afterwards. Are strip stars in binaries? The answer is yes. We detect binary motion in the majority of the strip star sample, which we analyze. So of the 8 systems, we find binary motion in 5 of them, and we have 3 non-detections, which I'd encourage you to ask me about afterwards. Here, this is a binary motion diagnostic plot. On the x-axis is delta RV max, which is the maximum minus the minimum shift that we observe. So this is a function of time, and this is the radial velocity, and you take the max and the min, and you subtract them. On the y-axis, this is the detection significance. So it's how much they shift divided by the error. And if you want to detect binary motion, you want a big shift and you want a big significance. If we impose some empirical thresholds based on previous works, we get 5 systems which are showing binary motion. And if you overinterpret a sample of 8, this is a binary fraction of 63%, which implies that the intrinsic fraction in the sample is at least 63% or higher with selection effects. Here are what the orbits look like for the 5 systems where we detected binary motion. First off, it's good that we get orbits for things where we detect binary motion. Nice confirmation. Few things to highlight are that relative to the shifts we're finding, which are, like 30 to 100 kilometers per second, you can see the residuals are on the order of 10 kilometers per second and don't exhibit much trend, which should hopefully convince you that our orbit fits are pretty robust. What do the properties look like? Well, for periods, we're getting periods that range from hours. So in the case of star 2 here, 16 hours, all the way up to almost a year in the case of star 1 with roughly 300 days. This huge range of periods across 3 orders of magnitude already starts to imply that we're seeing different binary interaction scenarios here, and there's not just one channel in this sample. Moving on to eccentricity, the orbits are consistent with circular. As opposed to previous works, which assume that post-mass transfer systems are circular, we explicitly allow eccentricity to be non-zero when we do our fitting procedure. This is what the posterior distributions look like for eccentricity across each of the stars we get orbits for. Qualitatively, you can see that these distributions are overlapping with zero, but quantitatively, we can compute something called the lower outlier threshold, and we can figure out that zero is not an outlier relative to any of these distributions. And as such, we don't find any strong evidence for eccentricity in our sample. Instead of quoting measurements, we therefore quote 95% upper limits, which pretty much rule out high eccentricities. So our upper limits range from 0.1 to 0.3. Now I'm going to try and contextualize the properties I just talked about in comparison to other observed distributions of binaries. So we'll start off here with massive OB binaries on the main sequence. You can see that the periods, these are cumulative distributions, by the way. You can see periods range from a day to several thousands of days, and the eccentricities display a wide range from circular all the way up to something like 0.8. These are pre-interaction systems. So these are very much the initial distribution of orbits. Looking at the strip siblings of intermediate mass strip stars, so the subdwarfs in pink and the Wolf-Rays in red, two important things to note are that mass transfer tends to shrink the orbit. So you can see that this tail, this high period tail gets shorter here. And on top of that, it is assumed that all of these orbits are circular because when they take a look at the data, it does seem to be the case that they are effectively near circular for all of the stars there. Additionally, just to show you how tight things can get, here are some white dwarf main sequence systems from Gomez and Moran, 2011. These are very short period because they were formed through common envelope evolution. And these systems can be something like hours to days for periods, and again, circular. So if you see something very short, this is probably telling you that it's common envelope. And finally, here are the strip stars on top of these distributions I just spoke about. The things to take away from this are that we are seeing periods which range from the shortest end for the white dwarf main sequence common envelope systems all the way up to the longest periods found for the Wolf-Ray plus O-star systems. Whereas we are explicitly trying to measure the eccentricities, but we nevertheless find this striking circularization which occurs from the OB populations. You see this dramatic shift towards effectively zero eccentricity. You can take the orbits of these strip stars and combine them with mass estimates from the primaries, the strip stars themselves. That's M1 in this equation. Then we also know P the period and K the semi-amplitude from the orbit fitting. And you can convert this into a minimum mass constraint on the companions in these systems, which is M2. We would really like to determine whether or not it's a low mass main sequence star or a compact object in these systems. That being said, none of these minimum masses are conclusively ruling out main sequence companions. And that's because most of the stars here we find in minimum masses on the order of like 0.6 to 0.9 solar masses, regardless of the strip star mass that we assume. So the x-axis and y-axis here are just different ways you can estimate the strip star mass. The fact that they roughly lie along 1-to-1 ratio here means that this assumption doesn't really matter, but the point is just that they are not that large. You might have noticed the outlier here, star 1, has a minimum mass of 3 solar masses. The thing about this system is that the strip star is very big, like 6-7 solar masses. And as a result, you can actually potentially hide a 3 solar mass companion inside of the optical spectrum. So that's a special case there. That being said, if these are genuinely living stars as the companions, the mass transfer which occurred almost certainly had to be non-conservative. Otherwise, we would blatantly see the signature of these stars in the spectrum. They'd be sp2s as opposed to sp1s. So to conclude, this is just the tip of the iceberg. I just talked about 8 stars, which come from a sample of 25, but we're soon going to move from tens to thousands of systems. So I'm just borrowing this metaphor from the first conference on strip stars from this past summer. The rest of my thesis is going to be focusing on some of the strip stars with brighter companions within the sample that Maria and Ilva found. Very soon, Bethany Ludwig is going to publish a catalog of thousands of strip star candidates in the Magellanic Clouds down to a solar mass, and this is going to be very useful for obtaining population rates. And then finally, we'd really like to find the galactic analogs, which we have not found to date. Few things on that front. We observed some candidates last week, which is nice. On top of that, there was a paper on the archive last week by Naz and Rao, who claimed a 4.5 solar mass strip star instead of a black hole imposter. And finally, within the SDSS collaboration, people are starting to look for strip stars in the BOSS optical spectra. So the future is hot and intermediately bright for the intermediate mass strip stars. And I'll leave it there and take any questions if there are any. Thank you.
Time for a lot of questions. Let's start with
last week, I think was given with a poem, so I could find a poem question. Was now my task. Yeah. It's difficult. Why is this the case? I must consult. Yeah.
Why is Bishop Arby's difficult? Okay.
The resolution we have with MAGE is lower than previous surveys for massive stars, and people typically employ something called cross correlation, which is when you take a template and you shift it relative to the observations, and you can compute something which should show a spike at the velocity where your star is genuinely at in the binary. The issue with this is that it can easily latch onto noise features in your data. And once you go below a certain resolution, you're subject to this. So as a result, instead, we do the following, which is we do something called template fitting, and in combination with bootstrapping to estimate radial velocities. So we first create these templates by stacking the data, and that gives us a really nice template to then shift across each epoch individually here. So each line here is an epoch, and each column is a spectral line, a Balmer line, or helium-2 line. And you can shift all of these lines in tandem and get these distributions of radial velocity. So that's the approach that we take. We think that this is more robust at the noise level that we have relative to the cross correlation. I hope that answers the question.
It's great. It's like if you use average, it doesn't look like it. We use it to be much more smooth than an average would be. Those averages are very distributions. We get noise of a given spectrum is in the spectrum and will correlate at zero, but that looks like.
Oh, I see. So sorry. So these distributions are not averages. These are from jointly motion moving the lines. Oh, the template. What do you mean by average in this case?
That the noise of your spectrum is in your average.
Oh, I see. So we do this. So to construct the templates, we do a noise weighted stacking where you prioritize the best observations and then you downweight the worst ones. So we think we maximize the signal we can get out of them.
Yeah, that's these ones would be your resolution. Lines are all results.
These are particularly good ones. There are some worse ones for sure. Yeah. Yep.
So what is the signal noise? You said
it's range from like 10 to 50, depending. Yeah.
So
we throw some stuff out that's on the lower end of that, but like 20 to 40 is probably the range that we're in. Yeah.
Precision usually get.
And show you can read that off of this plot actually. Sorry. So for something that shifts like 60 kilometers per second, we're getting a significance of 10. So that means like roughly 5 kilometers per second errors that we're getting. Yeah.
So you get signal.
Yeah, but it greatly depends on the amount of shift we see. Like you get way more significance on the shifts for the ones that shift the most. Yeah.
So in order to make this plot for detection with this binary, you really just need the two plot.
Yeah.
You can get that. Although maybe you are not getting the max. So you may want to extend on. But for the eccentricity management and orbital fit, you probably need multiple plots in order to get a good orbital fit. Yeah. So now that we have done 8 of them and you learn about the distribution, how that infer you to design the experiment for future rounds when you go from tens to 1,000 to make sure you are most efficiently getting those properties with minimized or minimal and how you think you would design such experiments Because if you go back to your next slides, I believe you have, yeah, these, but you may not need all of those eval in order to get into the orbit.
Yes.
You can teach them. So
Yeah.
what you feel you learn from what you have here to design a future experiment for getting the period eccentricity for. Maybe that's a cold question. I don't all the time. I'm just curious.
It's just hard to design an intelligent observing strategy when you have things that are orbiting every 3 hours and then every year, and you don't know beforehand what you're doing. So ideally, you just try to sample over as many frequency baselines as you can, and then you hope that you find the signal early, right? Because if you see something immediately that shifts within 2 days of each other, then you know it can be a short period, and therefore you don't have to do these longer baselines. But like in the case of Star 1, it took a year to figure out that it was moving at that time scale. So I'm not answering your question, but it's just hard. And I think that, I mean, I wasn't there for this, but I think Maria and Bethany and Ilva like tried to do like forecasting where you put the orbit forward in time based on what you think it might be. And I don't think that worked incredibly well. It like really takes 10 plus to like get to the point where you're confident, like as you can see. I mean, that's true. That's true. I think, I mean, with AAT it is. Yeah. That's what Bethany is doing. But yeah, this is all single object. Yeah. Yeah.
Any other question for Alex? Yes, Kevin.
Oh, the non-detections, sure. So, why might you not detect binary motion? You can have an inclination effect where you're so face on that you don't detect any of the shifts. You can be on a period which is comparable to your observing window, and therefore you wouldn't detect the shifts. Or you could not be in a binary. Those are the options you have. The one clue we have right now for what's going on with stars 5, 7, and 8 is that if you look at how much they shift, delta RV max is a function of the hydrogen surface fraction. This is how much hydrogen is left on the surface of the star in percent. You see a like ridiculously striking bimodality where all of the stars which are in binaries seem to be hydrogen poor, 30%, whereas all the stars which don't move much are effectively hydrogen free, almost zero. This is very surprising if it's just an inclination effect or just long periods. And this really points to these systems being fundamentally different in the binary interaction which produced them. Yeah, early days on figuring this out, but something weird is going on.
Any other questions?
Yeah. Yeah, I think it's, if you go down the route of assuming they're no longer in binaries, it could either be that it was a merger or an ejection which occurred. And I think there's some stuff to be learned from the subdwarf mergers where you have the extreme helium rich subdwarfs being merger products. And maybe we can learn something from there. And we can also potentially try to look at the proper motions of these stars relative to their local distributions in the clouds. The issue with Gaia measurements at this distance, though, is that they're not great. So I'm not sure that we'll be able to say something conclusive about like ejections off of that. Yeah.
Okay, so here for I just want to mention that I believe that for observation trips, there are not fun or about one of those. In addition to the conference, for the conference, I would encourage the grad student to consider taking opportunities to go observe like Alex and Stephanie did, and he did for actually going to another continent to get some data for their. Okay, let's say Alex again.